Okay, so this will not show up on CompreZoom because we're not using CompreZoom. It's going to save directly to my computer, and I'll upload it to YouTube, and I'll share the link with the class. So that's how you're going to get the Unit 13 stuff. Well, thank you for joining me. Welcome to galaxies. Galaxies are the big things. Element of the day, iron. There's a whole industry around iron built in the United States, and the faulting in that industry due to lack of modernization is a political hot point. I wrote that in 2016, back when such things seemed important before our entire economy got shut down for forever. Interestingly, iron itself is not particularly useful. It has to be mixed with carbon to make steel. Without that, even bronze was stronger. The reason that the Bronze Age came before the Iron Age, or whatever you want to call it, is that bronze will tear through iron until you figure out how to smelt it using carbon. From astronomers' perspective, the most interesting thing about iron is that it's the most stable element in the universe. And then, question for all of you: what causes a high mass supernova what causes a high mass star to go supernova? The moment that core starts to fill up with iron, it is doomed. The iron acts like an energy sink. It doesn't give you energy through fusion. It doesn't willingly break apart to commit fission. So it's basically sucking energy out of the core of the star. And stars rely on energy coming out of the core in order to resist the force of gravity. So iron's quite an important element for astronomy. There's the nuclear binding curve. We talked a lot about that in the high mass star class. Today we're going to do galaxies. Kind of fast, really fast. I'm super hungry. But I did look at the questions before the class started in order to make sure that I'm going to touch on all the topics that you'll be asked questions on. So there's the Milky Way. The Milky Way rises over Square Tower, an ancestral Pueblo building at the Hoven Wheat National Monument in Utah. Many stars and dark clouds of dust combine to make a spectacular celestial sight of our home galaxy. The location has been designated an International Dark Sky Park by the International Dark Sky Association. I started this class, well, second session's class, by saying that those of you who've never seen the Milky Way, owe yourself a trip out away from civilization to see it. But make sure you do it at the right time of year. The Milky Way isn't always visible. Anybody remember why and want to turn on their mic and say it? I'll give you a moment to get brave while I go over to the board to draw it. Okay, this is clearly not anything like to scale. But here's the Earth and the Sun and the rest of the galaxy. We're pretty close to the outside of the galaxy, which is a great place to be. And I'll talk about why that's the case during this class, actually. If you were on Earth at this time, could you see the Milky Way? What do you think the answer is? Anybody want to share via chat? Period enter if you're going to be brave. But we're down to 7 people. Okay. The answer is no, you would not. Because the sun is going to completely wash out the Milky Way. The Earth is sitting here, it's happily spinning 24 times every day, slowly going around the sun this way. And you've got to get to about here for the Milky Way to be visible even half the night. When you get to here, the Milky Way will be visible the whole night. Back to here, the Milky Way will be visible for half the night. Back to here, and the Milky Way isn't visible at all because when the Earth is facing the Milky Way, it is the time of day called daytime. So because we are at the outskirts, the Milky Way is only visible for part of the year. If we were very, very, very close to the center, you would see the Milky Way all around us all year round. We'd also probably be dead. There'd be no life on the planet, but minor details. Here is a stretched out version of the Milky Way with some weird perspective stuff done so that you're getting more than your field of view in the picture. And that is what we can see of the galaxy. Notice there's dark swaths all throughout it. I'm hoping by now that everybody knows what those dark swaths are. These big old bands of dust. Normal visible light doesn't go through dust particularly well. Infrared light does. So astronomers crave infrared satellites that can let us peer through that dust and see the center of the Milky Way. Unfortunately, our last infrared satellite has run out of coolant. So the inside of the satellite is now about the same temperature as the stuff it's trying to take a look at. That would work about as well as if your cell phone was glowing in visible light as you're trying to take a selfie. It just messes with the electronics. We got a new infrared satellite ready to go called the James Webb. It hasn't been launched yet. I personally think that it's going to get up into its position on the far side of the moon, far too far for us to fix it, and it's not going to work. But I'm a pessimist about such things. We try to build spacecraft without any one single point of failure, redundancy systems. The James Webb has about 100 points of failure. There's about 100 things on it where if it doesn't work, the whole telescope will be non-operational. So any one of those 100 things could give us a problem. And the atmosphere blocks infrared radiation for most wavelengths of infrared radiation, so we can't very well build infrared telescopes on the surface of the Earth and take pictures that way. So the dust is a real barrier for us. We've gone through this before. We didn't used to know where we're at in the galaxy, in the universe, they would have said at that time. And there was this big old argument called the Great Debate. And there was one point of view that said, I count about equal number of stars in all directions, so we must be the center of everything as far as stars go. And they were looking at the stars that were visible. The thing is that the galaxy is a big place. Yeah, there's about equal numbers of stars in all directions because with the strength of the telescopes they were able to use, they were indeed able to count equal number of stars in all directions. It just means the telescopes weren't that strong. They were looking at fuzzy objects in the night sky. If we were able to meet and use a telescope, I would show you such a fuzzy object. All you can really say about them is that they're fuzzy objects. At the time, they didn't know anything about them. It's just some section of the night sky that's a little bit brighter than the rest of the night sky. Some of those objects are nebulas. Some of those objects are galaxies. Some of them are globular clusters. They're all groups of stars that are so far away, or groups of heated gas, that we don't perceive them as being separate objects, at least not without computers and being able to look at them for a long time and add up all their light, get a sense of what kind of structure is really there. But the human eye just sees them as a fuzzy object. So they did have photographic plates, and so they could use the photographic plates and expose them for a long time and start to get some kind of visual image. So they saw objects called Messier objects like this, or like this. And what do these two things have to do with each other? At the time, it wasn't so clear. That's one kind of shape. This is another kind of shape. With the modern astronomical images, we instantly say, oh yeah, that's a galaxy. And that's some kind of nebula. It's a big old gas cloud. But to the people doing the research at the time, it really wasn't that clear, which helped to fuel the great debate. So in the name of saving your time and my time, I'm going to leave looking at the Messier objects for those of you who want to click on the links yourself. You have all the PowerPoint presentations. And it's interesting to look at both the original pictures that were taken with photographic plates and think about what that would mean to you if you were trying to interpret the objects and what the heck they mean. And also look at the modern astronomical images. Not gonna talk about the Herschels. So, early astronomers, by early we're talking 17th century-ish, thought the Milky Way was small and centered around the sun because no matter which way they looked, they counted the same number of stars. Unfortunately, there's a lot of stars that are so far away that they couldn't see them with the sorts of telescopes they had. The counter-argument for this came to fruition via Harold Shapley. So the first time I went through this, you didn't know what globular clusters are. But now we've done a whole section on it, and so now you know that globular clusters are gigantic, although not as big as galaxies, spheres of very old stars. They don't have a black hole at the center. They don't really have much structure excepting for being generally spherical. They're gravitationally held together by the gravity of all of the stars put together. Galaxies attract them and hold them. So Shapley went out there and he started counting globular clusters. And here superimposed are the number of stars we can count in all directions and the globular clusters that Shapley was able to see. Now, well may you ask, those globular clusters are hecka far away. If we couldn't count stars that far away, why could we see the globular clusters? Two answers. Answer number one, there are a lot of stars in a globular cluster. They are pretty darn luminous. The stars are all old by the nature of a globular cluster. They're basically the oldest kinds of stars we can see, but there's so many of them. Answer number two, the disk of the galaxy has a lot of dust in it, but if you start to look even just a little bit above and below the galaxy, that dust goes away. So Shapley didn't have to deal with the kind of extinction caused by dust that the people counting stars were doing. And so by looking at globular clusters, he made the argument, hey, these things are orbiting the center of mass of the galaxy, right? That was the only thing that makes sense if they were in orbit at all. And by counting them, it's really clear that they aren't grouped around us. So we must not be the center of the galaxy. There is a much simplified picture. So there's a sun, bunch of globular clusters. Ergo, we must not be at the center of the Milky Way. And that's about all I'm going to say about that. If you want to go back and review the argument in totality, I think it was unit 6 that I first talked to death in. I'm really not sure. I should name these units something by other than numbers. So, big debate. We can see these nebulous objects. Are they inside our galaxy? Are they outside our galaxy? Is the galaxy all there is? The debate rages. How far away are the spiral nebula? Shapley says, our galaxy is the entire universe. Spiral nebula are clouds of gas. The sun is not the center of the universe, but rather is a part of a cluster of stars, 50,000 light years from the center of the universe. The universe is 300,000 light years across. Curtis says, spiral nebulae are galaxies like our own, island universes. The sun is near the center of our galaxy. The galaxy is only 30,000 light years across. They both got some things wrong, but Curtis got it the most wrong. Shapley showed the Milky Way is larger than it was believed at the time, and the sun is offset from the center. But he was wrong in that the Milky Way doesn't encompass all these nebulae. Most of them, in fact, are physically outside of the body of the Milky Way. There are other galaxies. And Curtis's main contribution in being right was to argue the data available was not a sufficient quantity to conclude the spiral nebulae were inside of the Milky Way, which he was certainly right about. And at the time, astronomy did not have very good data at all. The person who solved the mystery is a gentleman named Edwin Hubble, working out of Flagstaff, Arizona. A rich guy. I think he married rich, actually. But however he got his money, he used it to build what was at the time one of the best observatories in the world, next to one of the darkest cities of the world. And he used this big old telescope to stare at all of these different nebulae and use photographic plates to discover their shape. And he came up with a general nomenclature of what these things are. Don't assume, because of the way that Hubble drew this, that elliptical galaxies either turn into unbarred spirals or barred spirals or anything like that. In the United States, we read left to right. And so it's tempting to think that, but it's definitely not the case. In fact, it is spiral galaxies that eventually turn into elliptical galaxies by colliding with each other. So here are pretty pictures of the galaxies. The Milky Way happens to be a barred galaxy. We now know that when a spiral galaxy has bars, those bars are not stable. They will eventually reform into the arms of the spiral galaxy. They are a result of matter being ejected from the core and shock waves being ejected whenever the central black hole of the galaxy eats something big. By something big, I mean a dwarf galaxy. So because the Milky Way is a dwarf galaxy, or excuse me, because the Milky Way is a barred spiral, we know that it has, within the last few 100 million-ish years, eaten a dwarf galaxy. As a matter of fact, we know it's eaten a lot of them. We can see the shock waves from the jet above and below the Milky Way. Our galaxy is a monstrous cannibal. It has ripped apart countless other galaxies by this point in its lifespan. From when Spitzer, the last infrared telescope we had working, this picture is from Spitzer, which was the last infrared telescope we had looking. And so if you could see through the gas and dust from where we're sitting in the Milky Way right now, you would see something like this. There is a big roundish cluster of stars at the middle, and the spiral is brighter closer to the middle, and it gets dimmer and dimmer and dimmer as you get further and further and further away. This is a guess as to what the Milky Way might look like if we looked at it from above. Because it is so very hard to see to the other side of the galaxy, all that dust, even with an infrared telescope, if you have it working, which we don't, we're not even 100% sure how many arms the Milky Way galaxy has. 3 is a pretty good guess, but I think that most astronomers would cop to the fact that we couldn't say that for sure. Our location is off of the Orion spur, which is a minor spiral arm located between 2 other arms. And then I need to make this picture bigger. Nope, still can't read it. I'm already covering the text. Perhaps I just need to delete this slide. So how do you get spiral arms? So you have clouds of irregular material close enough that they gravitationally attract each other. As they move towards each other, if they have any motion relative to each other at all, they're not going to directly collide. Instead, they're going to start spiraling. And over time, the spiral arms would form. But if this was the only thing that was happening, over time, the spiral arms would wind up and disappear, and you just have a flat disk. Since many galaxies have spiral arms, they must be long-lived, and there must be some other process to make them be maintained. More on that later. In the meantime, let's look at the other type of galaxy. Spiral galaxies are pretty new galaxies. Back to here, one slide ago. You see that they're formed out of just regions of gas interacting with each other. That's a relatively new galaxy. The other form of galaxy that we see out there, the big one, is elliptical galaxies. They are the old ones. So elliptical, spiral. Elliptical, spiral. Spiral galaxies are bluish. Elliptical galaxies are reddish. And we know now through the study of how stars age that when a stellar body is really red, it's really old, because all of the big blue stars have gone boom, which they do much faster than the big red stars do. So elliptical galaxy doesn't really have huge O-type, B-type, K-type stars in it, whereas spiral galaxies do, because those types of stars are being born all the time. How a spiral galaxy looks to us depends a lot on its random orientation. Some of them we see disk on, some of them we see edge on. Example, completely edge on and completely face on, with stages in between. They all have similar features. They all have spiral arms. They've all got a central glob, although not every spiral galaxy does have a central glob. I'll talk about why in a couple of slides. But all of these happen to have the central big ball in the middle. Here is a much bigger picture of an edge-on spiral galaxy. Slightly from above spiral galaxy. And there is a third type of galaxy. Well, there's innumerable ways of classifying galaxies, but I'm only going to talk about three. Spiral galaxies, elliptical galaxies, and here, irregular galaxies. An irregular galaxy is a catch-all term for anything that isn't a spiral galaxy or an elliptical galaxy. Most irregular galaxies are formed by a recent collision. When a galaxy is forming, it can look like an irregular galaxy, but if it's going to eventually become a spiral galaxy, we would, if we realize that that's the case, identify it as a young spiral galaxy. Irregular galaxies occur when two galaxies of roughly equal size hit each other. Like what's going to happen to us when Andromeda hits us around the same time that the sun is fixing to go boom. Well, sorry, G-type stars don't really go boom. Around the same time the sun is swelled up huge and is ejecting its outer gas into outer space and making a planetary nebula. When Andromeda and the Milky Way do hit each other, they are going to pass through each other and gravitationally disturb each other in a way that will cause them to lose those pretty spiral arms. They'll fall through each other, then be attracted back to each other, and their stars are going to be sent every which way. The gas clouds in each galaxy will interact. There'll be a huge burst of star formation. But that's going to be it for the creatively named Milkdromeda, because almost all the gas is going to be consumed in that collision. So we'll get a lot of new stars, we'll get a lot of new planetary systems, but after that, it's going to be pretty much the end of star formation for this part of the cosmos. The Triangulum galaxy will hit us eventually too, but much later. And as you recall, or perhaps not, those are the three big galaxies in the local group. So I said that elliptical galaxies are the old ones and spiral galaxies are the new ones. Here are some hints as to why we can conclude that. Hint number one, the orbital path of the stars. Inside elliptical galaxies, stars orient without any kind of direction whatsoever. So with spiral galaxies, the stars are moving in lockstep with each other around the center, all in a flat disk. Elliptical galaxies, the stars can be moving any direction. Spirals have lots of dust, and gas comes in many temperatures, including gas that is cold enough to form the kind of nebula that will give you new stars. Ellipticals have very little dust, and the gas is extremely hot and can't form stars. And finally, the color, which is the real big give. Spiral galaxies have blue stars. Elliptical galaxies don't. That's the number one rule in astronomy for how you can tell if a body of stars is old. No blue stars, it's an old body of galaxy. It's an old body of stars. So elliptical galaxies are galaxies that have formed via the collision of many other galaxies in the early universe. Part of the reason that there's not a lot of dust is that there haven't been that many generations of star formation. The reason the stars all have random orientations is that the galaxies had random orientations, they plowed into each other. Elliptical galaxies tend to have a lot more stars than spiral galaxies do because they are conglomerate. A spiral galaxy isn't the only way that intergalactic dust can come together to form star structures, but it is by far the most common way for a new galaxy to be born. Spiral galaxies is what physics and nature would like to form as you add small particles of new gas onto it, and the whole system acquires some angular momentum. There are other lesser galaxies. This is the Large Magellanic Cloud, only visible from the southern hemisphere, so-called because Magellan's crew was the first Europeans to record it. It is a small, irregularly shaped galaxy near our own Milky Way. And again, because it is so hard to measure the velocity of things perpendicular to us, even though we can really precisely measure its velocity towards or away from us, we aren't totally sure if the small and large Magellanic Clouds are in orbit around the Milky Way, if they are just passing by and temporary stellar neighbors, or if they're going to get close enough that the Milky Way will rip them to pieces tidally and cannibalize them. I'm not going to go into depth on Sepia variables too much, not as much as I normally would, beyond saying this. There are huge classes of stars out there that brighten and then dim, brighten and then dim, brighten and then dim. We think that all of these stars have qualities in common with each other, such that they're all about equally bright at their brightest and equally dim at their dimmest. That means if we can find them, and if that assertion is true, then we can calculate really precisely how far away something is. There's many different types of stars that do this, but Cepheids are the brightest of all of them, so they're the most useful. So if it is true that all Cepheid variables are about equally bright at their brightest and about equally dim at their dimmest, when we find a Cepheid variable in another galaxy, we should be able to figure out how far away it is by counting how many photons arrive at Earth. If lots and lots of photons arrive, it's close. If not very many photons arrive, far away. There's a real ladder of logic that's required in order to use Sepia variables to discover distances from galaxies. But astronomers will take any data they can get. But they'd rather have this. Type 1a supernova. Hopefully everyone remembers how a type 1a supernova forms. White dwarfs manage to acquire enough mass from somewhere, probably from taking it from a companion star, that their personal mass goes over 1.4 times the mass of the sun. When that happens, they explode. And when they explode, we think they all explode with about equal luminosity. And they're really bright. They can easily outshine the galaxy that they are in. So it's easy for a telescope to pick them up if the telescope is looking in the right location at the right time. If all type 1a supernovas are indeed equally bright, and we catch one, then we instantly know how far away the host galaxy is, and with much more precision than we could figure out if we were looking at Sepia variables. I said there was many different types of these. Let's look at an example of that. So notice Sepias are the brightest. They are at the top of the absolute G-band magnitude, which when I taught you about HR diagrams, I just call luminosity, or total amount of light it puts out. But there's other types that are dimmer that can also be useful to astronomers. Notice that they increase and decrease in brightness by quite a bit, and they increase and decrease in temperature by quite a bit. Different physical processes can explain why this happens, but in general, a good explanation for all of them is just that gravity and luminosity, gravity and the amount of heat and light the core is putting out, or heat in the form of light that the core is putting out, aren't in good balance with each other. So excuse me. So the amount of luminosity from the core and the amount of gravity is not in good balance with each other. This leads to the star going bigger, luminosity is winning, crunches back down, spans out, crunches back down, spans out, crunches back down. And it continues in that cycle for a while, for a few million or billion years. So like I said, we think all the stars that are members of the family have enough in common with each other that we can make assertions about how far away a galaxy is if we see those types of stars in the galaxy. So those are the two main ways that astronomers figure out how far away these galaxies are. And they are indeed not part of our galaxy at all. Irregular galaxies are also bluish, indicating locations of recent star formation. Regular galaxies are bluish because two or more galaxies just plowed into each other. And that causes a lot of star formation. But they're also done for, right? Like when two galaxies of similar size combine, that consumes most of the available gas in them. They're going to have a lot of stars, but it's also going to be their last stars, most likely, by and large. And as the two galaxies pass through each other, get pulled back together, the bluish stars grow old, die, and the whole system settles down to become something much more like an irregular galaxy, where all of the stars have random orientations to them. More galaxies collide with each other. Excuse me, I say it becomes something more like an irregular galaxy. I mean, becomes something more like an elliptical galaxy. The more galaxies collide with each other, the more you get this rounded galaxy shape instead of a spiral galaxy shape. Because the end path of all the stars does end up being kind of truly random. They aren't moving around in a disk. They end up flying in every which direction. If they're flying in every which direction, they're going to make a sphere. So here is our galaxy. Notice the sun is not all that close to the middle. It's about 100,000 light years from one side to another. If you enlarge a pancake in a DVD to the size of a galaxy, which do you think most closely resembles the thickness of the Milky Way? I'll let you think for 20 seconds, and then I'll tell you what the answer is. It's a CD. Spiral galaxies are really thin. On to the spiral arms. The spiral arms are sites of recent star formation. They contain giant molecular clouds, which is a kind of nebula that's got a lot of molecules in them, thick dust lanes, bright blue stars that have just been born. And again, when two bodies of gas start to interact with each other, they will naturally form a spiral like this. Weirdly, the stars that are currently in the spiral arm were not always there. The spiral arm is a kind of a density wave that goes through the galaxy, which behaves a lot like cars in a traffic jam. So when you got a traffic jam, which cars in the traffic jam changes, but the traffic jam itself persists. And so the spiral arms are moving through a spiral galaxy. They're actually moving faster than the galaxy itself is rotating, and they're driving star formation in the regions they move through. The bulge in the center is full of old stars. The disk around the bulge is full of younger stars. There's a kind of a halo, spherical halo, surrounding the entire galaxy that doesn't have very many stars at all, but the stars it does have are very old. Those stars are hanging out there in the spots where the globular clusters are orbiting around our galaxy, and maybe they're stragglers that got lost from the globular cluster. Maybe they're individual stars that were formed close to the start of the universe and they just never got absorbed into a globular cluster. Whatever their story is, there's a sphere of old stars that surround our galaxy. In general, the closer you get to the middle, the younger the stars. As time passes, it seems like the stars just age out and they go more and more and more towards the outside. When you've got a young, vibrant galaxy like the Milky Way, over time, planetary nebula and supernova explosions scatter heavy elements into the interstellar medium. Thus, there were fewer heavy elements in the Milky Way early on. So when we observe these old stars, they don't have as much platinum in them, or as much gold in them, or as much uranium in them as the young stars have. The young stars have simply had time to have the gas that made them soak up more and more and more supernovas. Our own sun has absorbed so many supernovas that we don't know how many supernovas it's observed. That's unusual for a star. Usually an astronomer can look at a star and say, zoop, 3 supernovas, zoop, 2 supernovas, zoop, 5 supernovas. We look at the sun and we go, meh, lots of supernovas. Probably only stars like our sun that is the product of many different supernovas could have a planet like Earth. where there are many and very different types of heavy elements in the planetary body. Now, let's talk about the weirdness in how the Milky Way moves. When you look at how planets move in the solar system, you get the perfectly reasonable result. The closer you are to the sun, the faster you're moving. Gonna guess this doesn't bug anybody after our discussions of Kepler's laws. So yeah, Mercury is moving faster than Venus. Venus is moving faster than Earth. Earth is moving faster than Mars. Mars is moving faster than Jupiter. Great. This hopefully makes sense. But this is not what stars in the Milky Way do. Stars orbiting the center of our galaxy all orbit at roughly the same speed. Why are stars able to maintain higher speeds further out in the galaxy? Does this mean there's a significant amount of mass in the galaxy out at its edges? So the red line is how we'd expect to see the motion if there was one strong central mass. And the Milky Way has that. We've got a central black hole with the mass of millions of suns or whatever it is. And the halo around it is another few millions of stars. So we've got a lot of mass in the center. But that's just not how stars in the Milky Way orbit. Instead, it doesn't seem to matter how far away you are from the center. They all move about the same speed. And one of the big mysteries of astronomy is trying to answer the question of what is making this happen. And that will be the topic of the next video lecture I give, which is going to be about dark matter. The most accepted explanation for why the orbits in the Milky Way behave this way is something called dark matter. The idea is that the Milky Way could orbit this way if it was sitting inside of a really big halo of diffuse matter that we can't see. So there's the disk of the Milky Way. That's where the globular clouds and those few stray stars hang out. Sorry, there's a halo of the Milky Way. That's where the globular clusters and those few stray stars hang out. The disk, the stewing star formation. You see the central bulge, black hole hiding in the middle. You'd have to have a huge dark matter halo around that to explain the orbits of the stars in the Milky Way. And there's really only two explanations. There's either a lot of dark matter out there, and that's what's causing the galaxy to rotate the way it is, or else there's something we understand about gravity that is wrong. And astronomers tend to think that our understanding of gravity is correct. And there's some mysterious thing out there that we can't detect yet. There's two basic theories, although one of them is pretty not widely believed by this point. One is MACHOs, massive compact halo objects, large dark objects scattered throughout the galaxy's halo. So maybe there's a lot of black holes, neutron stars, cold white dwarfs out there, big ice balls, take your pick. Whatever it is that could be out there that doesn't emit. People tend to think that it's not that by this point. Or it could be that we have some kind of subatomic particle that we can't identify that is just hanging out with galaxies. Because it does respond to gravity, but it responds to precious little else. The center of most black holes, the center of most galaxies has a big black hole in it, even elliptical galaxies. Irregular galaxies tend to have two or more black holes because that's two galaxies that have collided. The central black hole provides a structure for the galaxy to form around. we can detect the black hole in the center of our galaxy by watching how the stars around it orbit around it. They're all moving around this one tight spot. That would be where the black hole is. Some supermassive black holes are swallowing lots of material in the center of the galaxy, creating jets to the top and the bottom, like so much else in astronomy makes jets, like solar system formation makes jets, like black holes make jets when they consume a star, like neutron stars make jets. So the galaxy shown here is having a meal, and it's going to become a barred galaxy, for a while at least. The same way our galaxy just had a meal, and it is currently briefly a barred galaxy. Now, let's talk about where these supermassive black holes probably came from. There are objects out there in the night sky that are very dim but visible. And we can tell by redshifting that they are enormously far away. Like really, really, really far away. Given how far away they are, the amount of light that they are producing must be enormous. Just spectacular. This is the current working theory. In the early universe, everything was a lot closer together. So you had stars before you had galaxies. Some O-type star gets born, goes supernova real quick, like it likes to do because it's huge. And the bigger a star is, the faster it will go supernova and or end its life in some way or another. Leaves behind a black hole. That black hole is in a universe that's much denser than our universe. There's gas all around it. So it just starts to eat. As it eats, it makes jets. And it eats and it eats and it eats. Those jets are so powerful that we can see these things, even though they are enormously far away. Remember that in astronomy, enormously far away also means enormously long ago. Light doesn't travel instantly. These quasars are billions and billions of light years away from us, and yet we can still detect them. So they must be extremely bright and an artifact of the early universe. Probably most supermassive black holes have a story that's like this. They probably used to be a quasar. So cast your mind back, you have a big bang, eventually star formation happens. You have a huge star that's born out of the hydrogen and helium that's left behind. It dies very quickly, but then it eats an enormous amount of the gas that's available. And the universe back then used to be a lot smaller, and so it had an easy time attracting a lot of it. The universe continues to expand, and it reaches a point where these black holes no longer have an easy access to a meal, but they have become enormous by the time that they've lost their meal ticket. And so they become gravitational points of nucleation, where gas can go towards it and some of it can end up in orbit around it. Voila, a galaxy. There's a quasar that is imaged by the Hubble Space Telescope. That quasar is 9 billion light years away. One of them's a quasar, one of them's a star. That's, unfortunately, this picture didn't come with the information about how far away the star is, but probably the star isn't much more than 10,000 light years away, give or take. So let's pretend that's the case. There's one star that's 10,000 light years away and one quasar that's 9 billion light years away, and they're both equally bright. That's how much light quasars put out in their jets. They are monsters. And they're probably the source of our supermassive black holes, which the universe is just lousy with. By lousy, I mean they are quite common. Not that there's anything innately bad in the existence of supermassive black holes. Indeed, they make galaxy formation a lot easier. When a black hole has a meal, it creates jets. There's jets above and below the Milky Way of gamma ray emissions and X-ray emissions that correspond to our Milky Way having just consumed some kind of minor dwarf galaxy. Something ended up on an approach course towards the Milky Way, and it wasn't on a path where the black hole ended up taking it apart with tidal forces and putting it into orbit around us. Instead, it was more or less on a direct collision course, and the black hole just got it. Consequently, we see jets above and below the Milky Way, and we see the Milky Way itself as a barred spiral, which only happens after a spiral galaxy's central black hole has had a meal. This is why it's good that we're towards the outside. One of the reasons why it's good that we're towards the outside. Yeah, the jets do mainly go above and below the galaxy, but that's a lot of energy. Stars that are close to the center of the galaxy still get irradiated when processes like this happen, even though almost all the energy is going above and below. We are nicely situated in a quiet neighborhood of the Milky Way, and it's a good thing. So here is an actual astronomical picture of jets. In this case, the center of an elliptical galaxy has had a meal, and it's shooting jets off from it. Elliptical galaxies don't develop any kind of particular features after their central black hole feeds. But if you see the jets, you know it just happened. So quasars are a function of the early universe. You really need a lot of fuel to make them happen. So in the beginning, there weren't any, because we didn't have any black holes yet. We didn't have any stars yet. Then we have that first generation of stars, live and die. The very heaviest ones are going to leave behind black holes, and they're also going to die first. So you get a lot of quasars. Time passes, the universe gets bigger, everything gets further apart, there's less dust, well, there's less gas available to feed these monsters, and there's less and less and less quasars. If you could stand on top of the black hole in the center of the Milky Way today and rewind time 11-ish billion years, you would probably be standing on top of a quasar. Most of the supermassive black holes probably came into existence this way. We know that they got their mass somehow. It probably wasn't from consuming stars. It was probably from just sucking down enormous amounts of gas back when the gas was much thicker because the universe was much smaller. Here again is a local group. I'm not quite sure why I've included this picture, but there it is. So all those blue things are little galaxies, candidates for galaxies like the Milky Way and Andromeda and Triangulum to rip to pieces and consume. But the Milky Way and Andromeda and Triangulum cannot easily deal with each other. When they collide, Andromeda and the Milky Way are going to hit each other first. We will no longer be a spiral galaxy, we will become an irregular galaxy. At the time, far in the distant future, when gravity is starting to really win, and all of these galaxies are gravitationally pulled towards each other, and they're all hitting each other and going this way and that way and this way and that way. we will no longer be residing in an irregular galaxy that we will be in after Andromeda and the Milky Way hit each other, but we will evolve towards being in an elliptical galaxy. Elliptical galaxies are a consequence of lots of little galaxies eventually getting gravitationally attracted towards each other and combining. Notice they're all in different locations. As they all get sucked towards the center of gravity, they're all going to end up having their stars moving towards that place with different velocities in different directions. And eventually all those stars are going to be buzzing around the center of mass. Andromeda's black hole and the Milky Way's black hole will eventually combine. And when the Triangulum galaxy hits us, that black hole will eventually combine with the Milkdromeda black hole. And all the stars we have left will be buzzing around that center black hole. The burst of star formation that you get when two galaxies combine as irregular galaxies will long since have passed. All the blue stars we get when the Milky Way and Andromeda hit each other will have died of old age by that time. Only reddish stars will be left, a big old spear of red stars. And so where we are now will eventually be an elliptical galaxy, not a spiral galaxy. There's the Andromeda galaxy coming right for us. Triangulum galaxy will eventually combine with us too. And by comparison, there's a large Magellanic cloud going by us. Or maybe not. Maybe it's in orbit around us. Or maybe it's on a course such that the Milky Way will eventually pull it apart with tidal forces and absorb those stars. Only time will tell. The large and small Magellanic clouds are the brightest dwarf galaxies in the sky. Notice they look a lot like the Milky Way does, and for a very good reason. They're just a ton of stars all located geographically close to each other. And that's all the white band of light that the Milky Way is as well. Streams of stars and gas surrounding the Milky Way gives evidence that our galaxy has torn apart smaller galaxies in the past. All galaxies exist in clusters, which may contain up to 1,000 galaxies. And of course, if those clusters are tight enough, eventually those 1,000 galaxies will eventually be one very big elliptical galaxy. You just have to give it time. Another evidence for dark matter, beyond the rotation curve of the Milky Way, is that when galaxies collide, it's more like this than it is like this. Granted, when the Milky Way and Andromeda collide, they will do this kind of dance and settle out eventually into a new structure. But dark matter doesn't seem to really interact very much at all with other dark matter, except by gravity. But what does gravity do? It causes gravitational lensing. So in the bullet cluster, we have two systems that have collided, and they have somewhat collided like this. But the dark matter has just gone like that. And we've seen evidence of gravitational lensing in the dark matter that used to be associated with that system, both on the right and on the left. And so, yeah, that's part of the reason that nobody thinks that there's lots of unidentified neutron stars and black holes and stuff like that out there hanging around us for no reason that anybody can figure out. Because we've seen dark matter get decoupled from the galaxies that it used to be attached to, and we've seen that dark matter do gravitational lensing. So that's another line of evidence that we are indeed surrounded by a big old ball of something that we cannot detect. Astronomers can model observed distribution of galaxy clusters using computer simulations. Galaxy clusters will clump together in superclusters. Each one of these bright knots in the image represents a supercluster containing about 100,000 galaxies. Let me I cannot minimize Zoom when I'm recording the meeting. All right, whatever. We'll figure out a way around this. Okay. So we would expect galaxies to be forming in roughly equal numbers everywhere in the universe. One of the base assumptions in astronomy is that there's no place in the universe that's particularly unlike any other place in the universe. So you would see galaxies spread out about equally initially. But one spot would just happen to have a little bit more gravity than other spots. And the galaxies would then start to gravitationally interact like that. That's the source of the superclusters. This is what it looked like if you could fast forward over billions of years and watch them form. And that's why you get the strands and the voids in between the strands. One more time. So way back in time, everything was equally spread out, but very minor variations lead one place to have just a little bit more mass than other places. And if you give it enough time, that little bit of an increase in the mass will win. And you get some spots that have lots of galaxies and larger spots that have almost none. Let me show you a slightly different simulation showing the exact same thing. There you go, strands and voids. So that's how the universe self-organized on the level of galaxies. And we would be a very tiny portion of this box. We are in the middle of the Virgo supercluster. The Virgo supercluster itself is not even all that particularly big. Oops, sorry about that. So there's a Virgo supercluster that we are nominally a part of, and the local group is quite a bit of ways from it. As I've said, the Milky Way is on a collision course with the Andromeda Galaxy. The top level shows what Andromeda will look like as it's approaching us. And then the bottom level of images shows what we would be seeing as the two galaxies interact with each other and what our night sky would eventually look like when there's so many more stars in the sky. Now, keep in mind, the time in which Andromeda would be hitting us is about the same time that the sun will be turning into a red giant. So we would need to relocate in order to enjoy this particular field of view. But if we do manage to relocate, this is what we will see. So closer and closer and closer, collision, lots of star formation. All the blue stars die out. New stars settle into stable orbits around each other. Voila. I've shown you this picture before, but I just want to remind you again, because it's pretty remarkable to think about. This is how many galaxies Hubble saw when it looked at a size of the sky that is smaller than a grain of sand held at arm's length. So you probably don't have a grain of sand on your desk, but you got a salt shaker. Take your salt shaker, pick up a piece of salt sometime tonight, take that salt, hold it out this far away, and then imagine that there's that many galaxies obscured by that piece of salt. That's how many galaxies there are in the universe. We are crowded with galaxies. They're everywhere. Another simulation of the growth of filaments and voids from the Big Bang, when everything was pretty equally spread out, to today, when gravity's had time to have its way with things. Although not as much as it will eventually. We still have spiral galaxies, we still have galaxies that are separate from each other. Eventually, the universe is going to be full of only elliptical galaxies. Maybe a few irregular galaxies hanging around that just don't have the right angular momentum to form that sort of structure. Around the day, Neptune. Neptune can be seen with a normal telescope if you know just where to look. They say that Galileo marked it on his star charts in 1612 but thought it was a star. You can see it with the naked eye if you have really good eyes. It would only be confirmed as a planet 234 years later. One of the most interesting things about Neptune is it's got a moon called Triton that's basically identical to Pluto. It is only a little smaller, it is only a little less massive. Triton is in retrograde orbit around Neptune. That means instead of orbiting in the direction the planet spins, so a planet spinning like this, if you're in a normal orbit, you are moving like this. Titan is orbiting like this. This is gravitationally unstable. Titan will hit Neptune eventually. Any satellite that's in retrograde orbit around the object that is orbiting is going to spiral in and be consumed. Perhaps the most interesting thing about Neptune, to a physicist, is how it was found.
Reality, they really decided that he didn't want to wait 80 years, quite far away, came back in. And so the question that everybody had at the time of the discovery of Uranus is, what kind of orbit does it have? Does it go in a circle around the sun, like all the planets do, an ellipse really, but we'll call it a circle, or is it on a very elliptical orbit? The only way to figure out what kind of orbit it has is to sit and watch it year after year after year and see it as it goes around the sun. Uranus takes about 80 years to go around the sun. 80 years is a long time to wait. So, in about 1820, an astronomer named Alexis Bouvard in Paris decided that he didn't want to wait 80 years to figure out the orbit. He was going to go back in time and see if he could find it. So what he did is he would go back a couple of years and look at other astronomers' data where they had drawn where all the stars were. And he realized, hey, this person drew a star there, but there's not a star there anymore. That could have been Uranus. And he says, okay, if that's it, I'm going to now go back another couple of years. There's a star where there's not supposed to be one. And he put it there and went back a couple of years. And he went back all the way to, I'm going to show you this table just because you can't read it. He went all the way back to that very first thing on the top of that plot there. 1690 was the first time anyone had actually seen Uranus was 100 years before its discovery. And he has data now from 1690 all the way up to 1819. He went through this math that I'm going to now go through line by line. I don't even understand what all this is. Eugene probably does. You know what all this stuff is? He does. He's nodding yes. But the important thing here is that he has all the positions of Uranus from 1690 all the way up to 1819, and he proved in somewhere up here, he says in French, that it's on a circular orbit. He proves that it's really a planet. This is his big result. He also shows it's not quite where it's supposed to be all the time. The little pluses and minuses that you see here in the second column are how far away from where it's supposed to be that it really is, and it's kind of deviating here and there. And he does what any good theoretical astronomer does when presented with data that doesn't make sense. He decided that the people who were doing the observations probably were bad, and you shouldn't trust them. He actually says this here. It's difficult. I don't know. If you read in French, you can see where he says it up here. He does mention the possibility, however, that there might be something else beyond Uranus perturbing its orbit. He then actually gave his observations, gave his data to an astronomer also in Paris, Leverrier, and he said, you should try to figure this out. There might actually be something out there. Leverrier worked on it for a while and realized that he could explain these data very precisely with a planet beyond Uranus. Leverrier went to basically the French Academy of Science and presented his results, and they were all very excited, and they clapped in their very excited ways. Yay, nice job, Leverrier. And he was very excited, and he wanted them to go look for it because he could tell you exactly where it was. And it did not occur to them, I think, that you could use math to discover a planet. They didn't really think that this was reality. They really thought that this was a really beautiful mathematical demonstration that you could make the numbers work out, which is not the same as thinking that you can use physics and math to predict things. And he's like, no, there's really a planet. Go look, it's right there. And then so nobody in France would look for this planet. He finally contacted the Berlin Observatory, and they opened up their telescope, pointed to exactly where he said it was, and they found it the first night of his observations. There's Neptune was right there. And to me, these two moments, Uranus as the discovery of the first discovery of a planet, which just changes the way that people must have thought about the solar system. But Neptune, the first really good demonstration that math, this newfangled math and physics stuff, actually is describing reality. It's not just a cute trick to make calculations. You can actually find things you didn't know that were there based on this math and physics. And I think those two things were.
All right. So I've been using the spare cycles of my brain to think about what I'm going to do tonight. I think, unless there's an objection, the best thing for me to do for the class is to go back through my email and do the, look at all the emails people have sent me about, give me credit for this thing, or I uploaded this late, can you grade it, and stuff like that. And then try to knock down a few more problems on the final exam so that there's more of the final grade, so that y'all can make an informed decision as to whether or not you want to do the extra credit. And I will do unit 14 and 15 tomorrow morning at 8:10 a.m. I'll send out a Zoom link just like now, in case anybody feels like waking up and joining, but just like now, I will hopefully get a recording delivered to me very quickly, and I'll upload it to YouTube and share it with the class. So we are done, barring questions.